G'day, in this video we're going to start having a look at content that's covered in Module 7, the nature of light. The first set of concepts that we're going to be looking at is understanding light as an electromagnetic wave. So we're going to be looking at dot point 7.1, point 1, 2, and 3. We're looking at Module 7, the nature of light. Our first inquiry question asks us simply, what is light? And these first three dot points unpack some significant work done by Maxwell. And the reason why we're looking at his work first is because he was able to unify the concepts of electricity and magnetism. Today we know that light is an electromagnetic wave, but there was a lot of work and science done to get to that knowledge, understanding, and conclusion. And that's going to be our focus today. So some key learning intentions. We're going to be looking at the work of various physicists who use lots of different kinds of methods to attempt to measure the speed of light. And that body of work is actually quite closely linked to Maxwell's work to unify electricity and magnetism, and the overall conclusion that was made about the idea of light being an electromagnetic wave, through which Maxwell's theoretical work and the applied physics of all of these scientists who measured the speed of light started to come together. We're also going to be looking at a scaffold which we're going to be using throughout Module 7 and also throughout Module 8, which will help you to summarize a lot of the concepts that we are learning throughout the syllabus. Now, the first scientist I want to introduce you to is Ole Rømer. He employed astrophysics in an attempt to calculate the speed of light, while observing the orbit of Io around Jupiter, which is one of Jupiter's moons. He noticed that when attempting to measure the orbital period, which he did by analyzing the entry and exit time of the moon's eclipse, he noticed that depending on where he was in Earth's orbit, there were fluctuations in this measured value. His proposed explanation for these observations was that light essentially had to travel from Io to the Earth so that it could be observed, and that these delays were caused by the fact that if, say, the Earth was here at position K, the light would take longer to travel to K, say, compared to position L. While he was unable to observe Io at position E simply because the sun was in the way, he was able to use the rest of his measurements to estimate that there was a 22-minute delay in the measured orbital period of Io between his measurements at point H and his theoretical measurements that he would take at point E, again, if the sun was not in the way. Using the data at the time, he also knew the diameter of the Earth's orbit. So knowing both the diameter and the time delay between, he was able to predict a velocity using this distance and time measurement. And he gave that estimate to be 2.12 times 10 to the 8 meters per second, which, considering his method and the accuracy of the measurements at the time, wasn't such a bad estimate. The actual speed is about 3 times 10 to the 8 meters per second, so by today's standards, he was significantly off. But the most important thing to note about his work here was simply that Rømer suggested that light had a finite speed, that light did not just travel instantaneously. And this was a huge shift in thinking from what physicists of his time thought about light itself. Also to note, a better explanation for these fluctuations had a lot to do with the relative velocity of the Earth and Io, not simply just its distance. A while later, James Bradley also used some astrophysics to attempt to measure the speed of light. He was looking at some stars and noticed that the stars' position changed. Essentially, they went around in little loops, depending on the position of the Earth in its orbital path. This phenomenon wasn't unknown, but a lot of Bradley's work was focused on getting really accurate measurements and being able to predict the positions of stars. When he was doing this work, what he noticed was that no matter what his math said for the position of the star at a particular time, the star was always lagging behind a little bit. And this lag in position can be attributed to the fact that light is traveling from the star to the observer, and that takes a period of time. Therefore, the light that we're seeing is actually from the past. This difference in position measured by angles is referred to as stellar aberration, and by measuring the angle of this aberration and the orbital velocity of the Earth, James Bradley was able to also calculate a speed of light which was significantly closer than the one that Rømer came up with. However, Bradley wasn't the only person through history working on trying to measure the speed of light, and what a lot of people were attempting to do was execute a time of flight experiment, essentially meaning that you would measure the speed of light a little bit more directly and on Earth. Hippolyte Louis Fizeau was one of the first scientists to design and execute a successful method to achieve this. Essentially, what Fizeau did was pass a beam of light through a many-toothed cog. If I'm not mistaken, I think there were 720 tooths on this cog. And essentially, if there was a raised part of the cog, it would block the light. And if there was a dip in the cog, the light was able to pass through. So the light, went through a gap in the cog, traveled 8 kilometers to a mirror, and then all the way back. I think it was closer to 8.5 kilometers. And when it traveled back, it went back through the mirror, but something that's interesting, and this concept will come up quite a lot for the rest of the course, we have what we call a half-silvered mirror, meaning that some of the light is reflected and the other portion of the light is allowed to freely pass through. So some of this light that came back from the mirror was passed through the half-silvered mirror and observed here. Essentially, what Fizeau was trying to achieve was spin the cogwheel at a speed at which the light could pass through the gap in the cog, hit the mirror, return, and still pass through the same tooth of the cogwheel. Essentially, what he wanted to know was the maximum angular velocity for which this could be achieved. By knowing this maximum angular velocity, he was then able to process his data and got what we would consider now quite a respectable estimate, 3.13 times 10 to the 8 meters per second. Again, this number is off, but considering the rudimentary nature of his experiment, he did again do quite a sufficient job. Following Fizeau, we come to the work of Leon Foucault, who also did a time of flight experiment. However, Foucault's measurements were much more accurate. He used a similar method to Fizeau. Essentially, what he wanted to do was send light along a path, have it bounce back to the same location, and then be able to measure some sort of changing characteristic or feature that he could then attribute to its time of flight. So he got his light source and pointed it at a rotating mirror. At a particular point in the rotation, there would be essentially a beam of light that went to the mirror, bounced back, and by the time it came back, the mirror had rotated slightly further along, which meant that the reflection of this mirror did not bounce back directly at the light source, but was deflected in a slightly different direction. If Foucault was able to measure where this point was, he could then determine the angle between the incident light ray and the detected light ray. So if he knew this angle of deflection and the angular velocity of the mirror itself, he was then able to estimate the time taken for the light to travel from the light source to the rotating mirror, to the stationary mirror, back to the rotating mirror, and back to wherever the light struck his detector. And assuming that he knew the cumulative distance for all of this, he was then able to estimate and calculate for the speed of light, which he found to be 2.98 times 10 to the 8 meters per second, which at this stage was the most accurate measurement for the speed of light as we know it today. Beyond this early work, there has since been some other contemporary methods used. One was done by Louis Essen and his team, who used the resonance cavity method. Essentially, Essen was able to produce standing microwaves, and this was done inside a resonance cavity. Essentially, there was going to be an emission of microwaves, the microwaves then reflected back, and if we were to cause a standing wave, the incoming and reflected microwaves would overlap in such a way where they would constructively interfere with each other and create a standing wave. Now, we don't need to know all the details of the mechanics of standing waves and how they work, but we should be aware that we can have standing waves with different counts of nodes and antinodes. Nodes being where the wave remains stationary, and antinodes where we experience the maxima and minima. So assuming that Essen was able to produce microwaves of a known frequency, as long as he was able to generate the standing wave and he knew the length of the cavity, the number of nodes in the cavity as well, and as well the frequency of the microwave that he could produce. He can work all of that math backwards, determine the wavelength, and therefore the velocity of the light wave. Another modern method that we can use is laser interferometry. Again, we have essentially a half silvered mirror, or as it's called in this diagram, a beam slitter. Essentially what we do is we shoot some electromagnetic radiation into the beam splitter. That directs the light in two directions, path 1 and path 2. These waves bounce back to the beam splitter and are recombined, and the interference pattern can be detected. Essentially, we can make a few assumptions here. If both mirrors are exactly the same distance away from the beam splitter, then when the waves return, they're going to remain in phase with each other. And if they're in phase and they recombine, what we're going to see is lots of constructive interference and essentially maximum amplitude for the wave. However, if you were to shift one of these mirrors by wavelength divided by 2 difference, that shift would mean that, let's say, if we were to move this mirror half a wavelength further back, that when these waves crash back in, because they've had to travel that further distance, they're now going to be out of phase with the beams that are coming from path 1. And so when these beams recombine, they're going to cause a destructive interference pattern, and that destructive interference pattern will mean that there is nothing detected here at the end. Therefore, the differences in the distances between the two sets of mirrors can therefore be used to determine the wavelength. And again, if we know the frequency of the electromagnetic radiation that was emitted, we can therefore calculate for C. Now, all 6 of these experiments help us to understand a little bit more the nature of light, simply because it has a speed, and that speed is finite. The speed of light is one of its arguably most important characteristics, and was pivotal in verifying the work of Maxwell and his theoretical physics. Already in Module 6, we had a look at Faraday's law, which, by the law of induction, shows that there is a connection between electricity and magnetism through induction. However, this is only the beginning. Maxwell's work was able to combine many known equations that described electricity and magnetism and unified the two concepts. We will unpack the consequences of some of these formula a little bit more in class, but please let it be known that you do not have to unpack these in any amount of detail, certainly not apply any of them. The kind of maths that is behind Maxwell's equation would be seen in a second or third year physics course. But again, we will look at them in a little bit more detail during class as we investigate further. So these equations, we build this model a little bit further that helps to describe the interactions and behaviors of electricity and magnetism. So this model, these equations, and further work from there led to a few conclusions which are pivotal in understanding electromagnetism and light. First off, Maxwell was able to conclude that if you were to change an electric field, that there would be induction that occurs, essentially the generation of a magnetic field. And if there was a change in the magnetic field, that would induce some sort of electric field that causes a change in the electric field. And this cycle is repetitive, essentially meaning that electric and magnetic fields are interlinked and one produces the other. Furthermore, by taking his equations, he was able to demonstrate that these fields have a periodic or wave-like nature, and it's got to do with this cos element of both of the equations for electricity and magnetism. As we've seen previously, when we're looking at graphing cos, we see that there is this progressive increase and decrease pattern or nature to any function that includes cos. From the structure of these equations, we can also conclude that the maximum electric field happens at the same time as a maximum magnetic field. And that essentially suggests that if you have two waves, one of which that's electric and one of which is magnetic, that you will have your peaks lined up at the same spot, meaning that both waves are therefore in phase. It also tells us that the two waves oscillate perpendicular to each other, and that once this wave starts traveling through space, they're both transverse waves. So what that means is that the oscillation is perpendicular to the propagation, and that if both waves are propagating each other, that essentially the wave will propagate perpendicular to both the electric and the magnetic oscillation. And we can see that quite clearly here in this animation, that there is an oscillation of the electric field and an oscillation of the magnetic field, but the wave itself propagates perpendicular to both. Furthermore, with some analysis of these equations, he was also able to determine that the speed of these waves that he was looking at were determined by the permittivity and permeability of free space. These are two constants that we have used in the past. The permeability constant, or the permeability of free space, was used to calculate magnetic fields generated by currents, and the permittivity constant was used when looking at the interaction of two charges and the forces experienced by them. So these two constants are quite deeply rooted in our understanding of magnetism and of electrostatics. And this was the equation that he came up with here, that c, the speed of light, is equal to 1 divided by the square root of the permittivity of free space multiplied by the permeability of free space. And when you substitute this into your calculator, you will get approximately 3 times 10 to the 8 meters per second. Hopefully when we start reflecting from things that we looked at the beginning of the video, we should be beginning to make some clear connections here. And finally, what Maxwell also came up with was the idea that theoretically, these waves that he was thinking about, these waves that were being generated, could have lots and lots and lots of wavelengths. Wavelengths that were yet to be discovered. So there was a really clear inference that was made from Maxwell's work. He was unifying electricity and magnetism, and he was able to conclude, therefore, that there are electric and magnetic fields that could be self-inducing and self-propagating. These essentially are what we know as electromagnetic waves. Furthermore, once he figured out the speed of this electromagnetic wave using our c equals 1 over root epsilon naught mu naught, and estimated the speed of these waves, at least theoretically, to be 3 times 10 to the 8 meters per second, quite quickly cottoned on to the idea that other scientists were measuring the speed of light and getting values which were near identical. So with this match, the clear inference to make here was that these electromagnetic waves that he was theoretically coming up with were matched to known waves light. And that beyond that, there were other electromagnetic waves beyond the visible light spectrum or any other known type of light wave, which also existed or could exist and were yet to be discovered. So in class, we're going to be unpacking the measurement of the speed of light through classical and modern methods, as well as Maxwell's equation a little bit further. What's going to start happening in this module, as well as Module 8, is you're going to be looking at all sorts of different bodies of work, scientists, and their experiments. And it can all become quite a lot to try and contain and remember. And in the HSC in particular, as well as your trials, you're going to be asked questions where you're going to have to refer to these bodies of work or specific scientists. And so to help keep all of these ideas together and organize these thoughts in your head, what we're going to start doing is summarizing these experiments, the scientists and their body of work, using a structure which will be similar to this. It's essentially my first draft of what this table is going to look like. It may sort of change along the way. We'll see how we go. But essentially, every time we learn about new concepts, particularly if they involve certain scientists or experiments, they will get added as a new row into our table. And the things that we'll be focusing on is who was involved, when did it happen, what was their experiment or their body of work, what did their findings and conclusions come up with, and if we've got any other additional things to add, we'll have a space to put that in too. Thank you very much, everyone. In the next video, we're going to be focusing on applications of light and looking at the spectra of light and how we can apply it to a concept called spectroscopy. But until then, have a good one.